All right, let's dive into the core of machine learning. We're going to cover how to teach a computer to see the future, look at the big mistakes that can trip you up, and most importantly, figure out how to tell if what you've built is actually any good. Let's do this.
So here's the big question, right? We're all drowning in data, but data is all about what's already happened. How do we get a computer to look at all that history and actually learn from it to predict what's coming next? How does that even work?
And the answer, of course, is machine learning. But forget about writing a million if-then rules. This is totally different. It's more like teaching by showing. You give the machine a ton of examples, and you let it figure out the patterns all by itself.
Yeah, the key phrase here is learned from data. Think about it. For something like a spam filter, you're not telling the computer, hey, if you see these 3 words, it's spam. No way. You're showing it thousands of real spam emails and thousands of good emails and letting it find the signals. And pretty much all of this is in service of one thing, making predictions. Okay, but learning isn't just one single thing. It really breaks down into 2 main flavors that you're going to hear about all the time: supervised and unsupervised. And, the difference between them is absolutely crucial.
So it all comes down to the labels. Supervised learning is like studying for a test with the answer key right there. For every piece of data, you have the right answer. This email? Spam. This one? Not spam. The model's job is just to learn the connection. But with unsupervised learning, well, you've got no answer key. It's just a big pile of data, and you're asking the computer to find interesting patterns on its own, like maybe grouping your customers into different types.
All right, so we've got our labeled data, we train our model, and we're good to go, right? Ha, not so fast. This is where we hit what I like to call the Goldilocks problem. It's this super tricky challenge of making a model that's not too simple, not too complex, but just right.
So let me ask you this, and it's kind of a trick question. If your model gets a perfect 100% score on the data you trained it on, is it a perfect model? And the answer is a huge, flashing no. In fact, if you see that happen, that's when the alarm bells should start ringing, because it usually means you've messed up in a really bad way.
So, on one end of the spectrum, you've got underfitting. This is the too cold porridge. Your model is just way too simple. It's kind of like trying to draw a curvy, complex shape using only a straight ruler. It just doesn't work. It misses the whole point of the data, and it performs badly on everything.
But here's the one you really have to watch out for: overfitting. This is the too hot porridge, and it's a much sneakier problem. Here, your model is so complex that it hasn't just learned the important patterns, the signal. It's basically memorized every single little detail, including all the random junk or noise. So yeah, it looks like a genius on the data it's seen before, but throw it a curveball with new data, it completely falls apart.
And this is what we're aiming for: the just right model, the one that's smart enough to find the real underlying trend in the data and ignore the noise. Because when it does that, it can generalize. It can take what it's learned and apply it correctly to new situations it's never encountered. And honestly, that's the whole ballgame.
So that brings up a really important question. How do we actually know if our model can generalize? I mean, we can't just launch it and wait to see if it fails on new customers, right? We need a way to test its real-world performance before it goes live.
The solution is actually pretty straightforward, but it is absolutely critical. You split your data. Before you do a single thing, you take your whole data set, you carve off a piece, maybe 20%, and you lock it in a vault. That's your testing set. Then you train your model using only the other 80%, the training set. And only when the model is fully trained do you unlock the vault and give it a final exam on the data it has never, ever seen before. Okay, so the final exam is over, we've got the results back, but what does a good score even look like? Just saying, hey, it works isn't going to cut it. We need specific, hard numbers to really dig in and see where the model is winning, and more importantly, where it's failing.
And the starting point for all of this is something called the confusion matrix. Now I know, it looks a little complicated, but trust me, it's actually super simple. It's just a way to organize the 4 things that can happen when your model makes a prediction. Let's break it down.
First up, a true positive. This is a win. The email really was spam, and our model correctly flagged it as spam. Perfect. A bullseye.
Next, a false positive. This is a false alarm. The email was actually important, but our model panicked and called it spam anyway. This can be a really bad mistake. Imagine an important job offer getting sent to junk. Then we have the false negative. This is when the model just flat out misses something.
A spam email comes in and the model says, nope, looks good to me, and lets it right into your inbox. It failed to do its one job.
And finally, the true negative. This is another kind of win. An important email came in and our model correctly identified it as safe and left it alone. So anytime your model is right, it's either a true positive or a true negative.
Okay, now that we have those 4 counts, we can start doing some math. The first and most obvious metric is accuracy. It's simple. Out of all the predictions we made, what percentage did we get right? But you gotta be careful, because accuracy can be super misleading, especially if you're looking for something rare, like credit card fraud.
And that's exactly why we have other metrics, like precision. Precision answers a very specific question. When my model flags something as positive, when it raises an alarm, how often is it actually right? Think of it as a measure of quality. High precision means fewer false alarms.
And the flip side of that coin is recall. Recall asks a different question. Of all the positive cases that were really out there in the data, how many did my model actually manage to find? It's a measure of completeness. High recall means you don't miss much, and there's usually a trade-off here. If you crank up your precision, your recall might go down, and vice versa. It's a balancing act.
Phew, okay, that was a lot, I know. So let's just pause for a second and boil it all down to the absolute must-remember takeaways from all of this.
If you remember nothing else, remember these 4 things. 1. Overfitting is the ultimate bad guy. Your goal is always a model that generalizes, not one that memorizes. 2. To check for that, you must split your data, no exceptions. 3. Get comfortable with the confusion matrix. It tells you how you're wrong, not just that you're wrong. And 4. Pick the right tool for the job. Accuracy is not the whole story. You have to think about what matters more for your specific problem, precision or recall.
So there you have it. That's the basic cycle of building and, more importantly, evaluating a machine learning model. It's the foundation for just about everything else. Which kind of leaves us with a final question for you. Now that you know how to tell a good model from a bad one, what's the first problem you'd want to solve? Let us know what you think down in the comments. And hey, if this was helpful, make sure to subscribe for more explainers like this. Thanks for watching.